Alright, kelas, boleh dengar saya ke, kelas? Okay, someone, you record ke? Ijan. Okay, thanks Ijan. Alright. Okay, for today class kita continue. If you look on your fatigue analysis, today we discuss about sample problem. If you look on your e-learning, I share you the e-learning. Okay, if you look on your e-learning, I already put here on the in-class exercise. One in-class exercise. Let's look on the Alright, Kak, you boleh nampak in-class exercise tu, you boleh, can you see the question 1 class question 1 Alright, question 1. So you can look here lah, one in-class exercise. Yang ni, the first one is your notes. This one is the solution for this question 1. You can look on that. Alright, okay, the typical, itulah I mentioned to you, remember that for your, if you look my live video, you can see my live video ni. Hold on. Okay, we know about itu dia apa tu, for our endurance for fatigue analysis, we know the basic equation. Normally in fatigue punya assignment or maybe your exam test question, you need to find the safety factor lah. Of course, we know based on Goodman, and based on Goodman line, the safety factor is like this. So your sigma E amplitude over your SN endurance limit plus your sigma EM over your SUT equal to 1 over your safety factor. So this is your safety factor, then you can get your safety factor lah. I already explained to you previously the SN. Okay, we can calculate SN, we can get SUT because material, SUT material is given. Okay, material, upper material, AISI 1040, you can, 1040 hot roll, for example, you can get the material, what is your tensile strength in megapascal. So you can put here in the denominator here. For your endurance limit, you have to calculate. So endurance limit, you know, is endurance limit is CL, CG, CS, CT, CR, and your SN prime. Okay, SN prime is a standard specimen test, fatigue test, Arnold test. So we know that our SN prime is 0.5 SUT. So we can calculate, since we know our SUT, let's say 960 megapascal, 0.5 of it. Okay, 400 ni lah. Okay, 480 apa ni? 400 ni 430, for example, at 0.5 SUT. So CL we can get directly, load factor, size factor, gradient factor, the size of your shaft at point that you analyze. Surface factor is the quality surface of your shaft. Temperature factor is the temperature during operation, and this one reliability factor is given. Its reliability is in 99%, you can get 0.897 if you're not mistaken. If not given, reliability is 1. If not given, is 1, because 50% reliability is 1. Not given, it means reliability is 50%. So you can directly get your SM value. So you can have the denominator. The only thing for us to get is our sigma EA and sigma EM. Okay, sigma EA and sigma EM. That's the only thing we need to find. Okay, privilege has shown you the sigma EA, sigma EM is you punya based on DET lah. Okay, you know DET. DET you punya, kita based on sigma, because we always has amplitude and mean. Always, in case you can find what is the amplitude, what is the mean stress. Okay, what is the mean and amplitude. If you look on your textbook, if you can see my textbook ni, okay, textbook on chapter 8, we can get, kalau combined stress, biasa normally shaft you have combined, you have bending, then you have torsion, and maybe you have axial. The sample problem we are going to discuss right after this, we have combination, we have axial stress, we have torsion, and also we have bending. Okay, remember in your textbook, when we have combined stress, you have to take point consideration. It means, okay, combined stress, okay, kalau you have biaxial stress, you have a combined stress, you got to find apa tu, By exercise, I mean you have significant and you have torsion stress. Online class, video. Ya, kelas, can you hear me? Boleh dengar kelas? Okay, video dia kan seolah je. Okay, video nampak my live video Okay, if you look, can you see my textbook Textbook on the page ni, you kena take note about the equation. 30. Okay. Normally shaft kita add element tu kita always by axial stress kita ada tau xy tau xy and tau xy because of torsional of that shaft, and also kita have sigma x. Okay, sigma x. Rarely in shaft kita have sigma. This is what we call biaxial stress. Rarely kita have more than that, sigma x. Sigma x ni sometimes guys, normally what in our case shaft, sigma x only is based on bending. Sometimes we have sigma axial, axial combined with bending. Because for the sample problem we will discuss later ni, we have combination. We have axial and bending stress. Sigma, there will be total your sigma x. But we always have torsion at point consideration. Sometimes we have torsion, sometimes not. Tapi most of the case we look at the point we have torsion, yes. This is what we call biaxial stress. Kalau biaxial stress, if you look on this equation in your textbook, sigma EA, so you got to find the sigma EE because equivalent stress DET, because base ET, sigma E amplitude, amplitude equal to sigma amplitude square plus 3 tau amplitude square. Okay, and sigma E mean, ini yang kita kena, because this one, EA, we have to put here at the denominator here, sigma EM, we have to put here, then we can get the safety factor. The sigma EM is based on the equation, page 301, guys. Take note in your textbook. You highlight the one. Sigma mean over 2 plus your square root, your tau mean square plus sigma mean over 2 square. So you got sigma. So you put into this denominator, then you can get your safety factor, either you punya point of analysis. Excuse me. Sorry guys. So this will be your safety factor. Boleh nampak video saya? Then you put, then you get your safety factor. Okay, tetapi another thing that saya tak consider, okay, kita discuss example. Kita punya fatigue stress concentration factor. Okay, fatigue stress concentration, because actually guys, okay, class, sigma EA ni, you punya sigma EA ni, all your stress here, like punya stress ni, you punya stress sebenarnya, you kena consider in shaft ni, normally shaft. Kalau sebenarnya shaft, okay, let's say you have a shaft here. This is your shaft and this is your shoulder. Okay, ini you have bearing at A, then mungkin you have pulley at B. A is bearing, pulley at B, and this one other point here, and mungkin you have another point here, you have C point here. Okay, okay, when you remember you plot your moment diagram, then you have maximum at B, and this is why you mount your pulley. The center line is your pulley. You have moment diagram like that. So you found that this one is a critical moment at B lah. So this one will create bending stress. Yeah, this one will create bending stress. But kita punya point of interest, we need point to consider here at the shoulder. Maybe we have at a distance 20 millimeter to the right at shoulder here. This shoulder, guys, if you zoom in, shoulder they have fillet radius here. So this is what we call stress concentration will happen there, because once kalau we have a fillet radius, or maybe at some point here we have a groove. A groove ni where is something like this. The shaft tu dia ada groove, dia ada lekuk. Dia ada groove, because the groove is where we mount our washer, snap feed, washer, a ring, a washer to lock the pulley, because B is where our pulley, where we have greatest moment. So this why actually there's groove ni where actually is not so in your Ferry Rock, and there's no washer, just to make sure that groove to, it means we have a snap fit ring here to lock the pulley. So this kind, like the shaft has a groove here, and they have a small radius here. Also here, the fillet at shoulder, also they have the small radius. This is our point of interest that we need to consider. But based on our moment diagram, so we have to consider this one. Moment diagram that we got maximum, even the maximum is at B, at this moment 1, we have to find it on our diagram. Also at moment at 2. So you can get this value by theorem Pythagoras. So you know the value of B and you know the distance here, you can get your M1. Also M2 you can get. So this is our point of interest. Actually, the weakest point along your shaft, even your moment maximum is at B, actually, the weakest point actually, it will feel is at the shoulder because we have a fillet radius here and also we have a notch radius. So we have 2 points that we need to consider. At point here, M1, where we have a groove, and also here at the shoulder here, we have a fillet. That we call concentration. Because why? Concentration, stress concentration, for example, you have a shaft and you have a groove. You have a groove. You have a groove. Kalau you punya shaft is not just a plain diameter, you have a groove. Groove ni where we put washer, macam to lock, washer, a ring, snap fit there, you will lock the pulley to be not misalignment. Go. Hold on. Yeah. Sorry. Sorry. Okay. The groove ni for you mount the washer like a snap fit ring to prevent the pulley to be sliding to the left lah. And this one it will be locked by the shoulder here, right? So this kind of shaft ni, kalau macam you have groove here, so you have a small radius here. You have a small radius there, and you have a small d diameter here because deduct the d is your major diameter. Small d is after you tolak 2 times radius lah. You have smaller diameter and bigger diameter. So this they have concentration. Kalau katakan this one have bending, have moment. Kalau katakan you bend this thing, and this is your neutral axis. Normally kalau is plain diameter, you punya stress distribution at that point tu, because since we have not, stress distribution of this bending stress, it become larger. Actually at normal we have 0, right? Tetapi at that notch tu, it becomes so high, dia macam stretch like this. Kalau normally kalau you just plain diameter, kalau just plain diameter, kalau axis, nothing. But if you have notch, you punya stress distribution, because of that curve, that notch tu, sorry kalau you have notch, you punya stress distribution is larger is larger. Kalau you have notch, you punya stress distribution, kalau you punya stress distribution at this notch it become lagi distorted. At neutral is 0, and at the notch it become lagi distorted. It increase more lagi compared to without notch, just a plain diameter. Stress distribution is much larger. Not just bending based on moment. You have bending like this. Also for axial stress also. F axial, you punya stress distribution becomes so large because of that notch. Not just notch on the groove, also in the case of you have shoulder. Okay, you have shoulder like this. You have bigger diameter, you have small diameter. So this is your shaft because shoulder, shoulder. You have radius here, and you have big diameter here, and you have small diameter there. At this shoulder, okay, this is your neutral axis. Kalau you apply axial stress, also bending stress, the stress distribution here at the notch here, at shoulder too, because we have a curve, the distribution of stress is more larger. They become more distorted. This neutral axis, let's say bending stress, this one compression side. Tapi at the notch ni, it becomes distorted lagi, larger than normal, without larger than in case smaller diameter ni just a plane. Because we have steps in it. All this curve, like this notch, we have a groove. It makes that we call stress concentration happen at that notch. So that is your weakest point. In this case, kalau you can analysis like this is your weakest point. Point of interest is here and here at shoulder, not actually B. Even why B, even D is maximum. Maximum. Even walaupun here maximum at B, but you can consider this one. You have to analyze also at this groove here and also here. So to get that moment at that point, you can look for your moment diagram. By theorem Pythagoras, you can get the distance. That's why I highlight too. So it means that the stress that you calculate, okay, the stress that you calculate, macam sigma, all your sigma amplitude, all your sigma, macam your bending stress. So it means that your bending stress, the bending stress that you calculate, okay, can you hear me guys? The bending stress, okay, normally bending kita calculate is 32 moment pi d cube, pi d cube. In this case, kita ambil the smallest d lah, the smallest d. Kalau this one, kita ambil the smallest d, pi d cube. Okay, kita ambil the smallest diameter because this is the weight case. The inside is the smallest diameter. This one is a bigger diameter. Tetapi because we have stress concentration factor, all of our stress, even our axial stress, this is bending. Axial stress is 4F. Kalau kita ada external force here kan, 4F over pi d square. So and also torsional stress. Torsional, sometimes we have torsion, right? We have torsion like this, torsion like that. Our torsional stress is 16T over pi d cube. So all these things have to kali Kf, have to multiply by Kf. That's all I have to tell you, kali Kf, kali Kf. So what is Kf? Everything has to multiply by Kf. Kf is your fatigue stress concentration factor. Because semua you punya stress ni have, kalau you punya case at point that you analyze at point here, at point 1 here, they have notch ni, you have multiply you punya stress that you know at M1 here, 32 M1, bending stress 32 M1 over pi d, diameter of this, the smallest d here. And this one bending at here is 32 M2 over pi d, yang smallest d here, pi d cube. But this one you have to multiply by its concentration factor based on shoulder case. This one you have to multiply the fatigue stress concentration pressure based on the notch punya case. I show you in our sample problem. I hope you understand what I'm talking about. So all of this is have to multiply. Okay, yang ni KF yang bending stress tadi just now, bending is 32 moment pi d cube have to multiply by KF bending case. Axial stress that you calculate, if you have axial stress on your shaft for F over pi d square, smaller diameter of your shaft, times fatigue stress based on axial. Torsional stress, your torsional stress along your shaft tu, you punya 16 top over pi d cube of your, the smallest diameter of your shaft times Kf based on torsion. So you have to apply this. So what is this Kf bending, Kf axial, Kf torsion? So the basic equation of Kf is like this. Basic equation, your Kf, you need to find Kf, the basic equation is Kf is 1 plus your Q times your Kt minus 1. Okay, Kt minus 1. So 1 plus Q Kt. This one in your notes, guys, you can check in your note, in your e-learning, I mention 1 plus Q Kt minus 1. If your case is bending, you mean your case Kf is bending case, you kena 1 plus Q, okay, Q ni base is on bending, times Kt also you have to find based on bending, minus 1. That is the case, okay. Kalau you punya case is axial, Kf axial equal to 1 plus Q based on axial, times Kt based on axial, minus 1. Kalau you punya case is torsion, Kf torsion equal to 1 plus Q torsion punya case, based on torsion times Kt based on torsion minus 1. Okay. So how the basic equation is here, basic equation. Your fatigue stress concentration factor is 1 plus Q Kt minus 1. What is Q? Q is your notch sensitivity. I show you a little bit on our sample. Notch sensitivity. Okay, sensitivity. And Kt is your static stress. Pasal kita now go for fatigue, static stress concentration factor. That is your concentration factor. Pasal yang kita find first is static stress concentration factor, but we have to minus 1 times Q plus 1, we get the fatigue stress. Kita adjust to the fatigue stress punya concentration factor. Okay, I hope you understand. This Kf can have to multiply to all your stress. Then your stress will be substitute into your equation sigma A ni lah. F to what is the amplitude, what is the mean. Okay, so that stress that will be put into this to calculate your safety factor, to calculate your safety factor of here. Okay. Alright, kalau you still not understand what I'm talking about, okay, kita go for this sample case. Go for this sample case. The exercise now I mentioned. Exercise that I mentioned. Okay, let's look at the exercise. Okay, class, you can still, my live video still on. Okay, the exercise, can you see question 1 in class? Class. Okay, question 1, this is a sample exercise of fatigue. Okay, it given the shaft, can you see the shaft O, A, B, C? Okay, the shaft, okay, you have 2 pulley, 1 pulley at this, okay, like, okay, this kind of question simple, we only have XY plane, right? If we XY plane on top plane. Okay, just because the pulley 2 kilonewton is one direction, okay, it's only at one plane, and pulley B also one direction, it's only one plane. Let's say X, Y, Z. So it's pointing on Y lah, both is Y. So our plane is only one plane, XY plane. We don't have exact plane. Along the shaft is X direction, right? Okay, this shaft is O, A, B, C. O and C is bearing, is said, bearing at O and C, support bearing at both end, O and C, and at A and B is pulley. Okay, smaller pulleys at A and bigger pulley at D. And it's given that pulley B, okay, is given the 2 kilonewton here at A and 0.3 kilonewton here. Okay, we have two tension at back. And the pulley at B, we have T1 and T2. And it's given that T1 is 0.5 to 0.15 T2. So we can get our T1 and T2 lah. We can get our T1 and T2. Okay, now the question asks, okay, the working temperature is 200 degrees Celsius. While this one is shaft in operation, the temperature is 200 degrees Celsius and the reliability is 90%. Okay, 90%. Remember, reliability, you can get your CR, reliability. Okay, and temperature 200 degrees Celsius is below 800, apa tadi dalam your tool, below 780 or 840 is the temperature is CT is 1. Nanti I show you later. You can get CT temperature, CR is 90%, is 0.894 if I'm not mistaken, for 90%. If I'm not mistaken, or 0.87. Okay, let kita check later. Okay, that one for CR and CT get. Okay, okay, determine whether the shaft will have infinite length. Okay, now we want to check. The shaft will have infinite. It means we need to find safety factor lah. Kalau you, okay, you know your safety factor sigma E amplitude over your S endurance limit plus your sigma E M over E mean. This one alternate amplitude, and this one is mean over your SUT equal to your 1 over your safety factor. Then you find out, you put all the value. If your safety factor is greater than 1, so the shaft will have infinite life. Remember, kalau safety factor than 1, it means because kita design for infinite life. All this equation endurance limit is designed for infinite life. If safety factor is greater than 1, it means the shaft will go for infinite life. It means 10 to the power 6 and above cycle, infinite life. Kalau the shaft fail to, it means they go for finite. So that is a formula for you to find how many circuit will fail. Itu later on lah. Tapi this question asks here to find the safety factor lah. If you get one point something, it means the finite life. Kalau you said the safety factor N is less than 1, so you answer the shaft will have finite life lah. It's not infinite. So the point is to get the safety factor. Okay. So the step that we're going to do, the first thing, okay, if we have this kind of equation, okay, this assignment for the shaft, okay, we know the shaft. Okay, the shaft is like this. Okay, this is your shaft, right? So we have at O here, and we have A here, and we have B, and we have C, we have bearing. Okay, we have bearing at C. Okay, and now we have at A2, we have pulley. Okay. Okay, hold on. Nampak ya? Okay, sekarang ni we have pulley at A. Okay, we have pulley at A. So this is all pulley. Okay, let's consider, because this one dia tak bagi axis. Let's kita put the axis like this. This is X, and this is Y, and up is Z. Okay. So we have tension pulley at A. We have in Y direction. One we have 2 kilonewton. Okay, 2 kilonewton, and one we have all in Y direction. Y direction is 0.3 kilonewton. And at B, we have a pulley, a bigger pulley at B. Okay, we have a bigger pulley at B, and it's given that this one is T1, tension 1, and tension 2. Both is in Y direction also. Then it's given that your T1 equal to 0.15 of your T2. Okay, be careful. This shaft, okay, this is not the normal case punya shaft. They have an external load. Be careful. So this shaft ni, they have external axial. They give that, this one the P. P is 2 kilonewton. Okay, let's say I put it F, force. Force is external axial. There is a case shaft where you punya ujung ni, that is an external load. It's pulling the shaft. F is 2 kilonewton. It both the same lah. Both the same. 2 kilonewton. 2 kilonewton is pulling the shaft. So it made the shaft also have axial stress. Be careful about it. So you have a combine your sigma tu actually, and which one point yang critical. Normally you buat your case you don't have axial force, but this one you have. Normally you buat shear diagram, moment diagram, and what is your maximum moment. For example, like A is the maximum, then you have a bending stress in direction is sigma x, but your sigma x have both sigma x based on bending 32 moment pi d cube plus that 4f over pi d square of this axial load. It means axial stress is uniform along the shaft, either O, A, B, C is along same axial stress. So it means our sigma to have to add bending stress plus axial stress. That's your element at A. Kata let's say A is critical. Okay, that is the case. Alright, so okay, it's already stated. All the dimension is given. Yang A ni given from A semua is dimension is given. Is given this one from O to A is 250. This one A to B is 450. And this one is 300 millimeter. Alright. The question asks you to find the safety factor based on this fatigue analysis lah. Either is finite or infinite life. Okay. So okay, what is the first step? It's already given the material of the shaft. Our kita is doing analysis on the shaft. The shaft material is already stated AI SI 1045 hot roll. Okay, hot roll. So you can get your SUT. So you can what is the value of SUT of your shaft lah. Okay, the first thing kalau you have like this, okay, you punya first step First step what you should do, apa kita punya first step kalau you have like this? Kita buat free body diagram, shear diagram, moment diagram lah. Betul lah guys? Hello class? Are you listening or not? Okay, kita buat the hold on. Kita buat the shear diagram and moment diagram. So shear diagram, moment diagram ni macam mana? Can we solve of T1 and T2? Of course you can. Macam mana you solve T1 and T2? This one 0.2 kilonewton, 0.3 kilonewton. Okay, the diameter of the pulley at A is 200 millimeter. Diameter at pulley B is 250. Remember, torque times the radius times 100 lah. Yang ni times 125. Okay, to get T1 and 2, we know T1 is 0.15 T2. And so to get to first, we got to solve T1 and T2 first, and then only you can make sure. Okay, let's say because our X is this direction, this is X kan. Okay, jadi kita cakap macam ni, X positive like this, X positive summation torque X lah, positive equal to 0 must equal to 0. So we got okay 2 kilonewton ni times positive X or negative X. 2 kilonewton times the radius 100 because diameter is 100. Are you listening or class? So 2 kilonewton ni produce apa? Positive or negative? Class. Are you with me or not? 2 kilonewton. Summation of torque is 0. We want to get T1 and T2. 2 kilonewton ni is positive torque or negative torque? Yeah, you're right. Positive. Okay, 2 kilonewton. I put it 2000 because we Newton millimeter, right? 2000 times the radius is 100 positive. Okay, the 0.3 kilonewton negative lah, kan? Negative, Negative. 0.3 is 300 Newton times 100. Okay, now T1 times radius ni 125 because diameter is 250. T1 ni produce negative ke positive? Torque. Plus. Hold on. Kau boleh nampak? Okay, T1 ni produce positive or negative? Negative, Okay. T1 produce negative, okay? Video saya ni nampak kan? T1 produce negative. Minus T1 times 125. Diameter is 250, 125 is the radius. Then T2 produce positive. Betul lah kan? T2 plus T2 times 125 equal to 0. Okay. We know that T1 is 0.15 T2. So from here we can get T2. So the answer of T2 I just to make it short. So if you look on the solution, your T2, we got our T2. Excuse me. Our T2 is 240. Then we know T1 is 0.5 T2 and T1 is 1600 meter. Okay, 1600 meter. So this is our T1 and T2. So It means T1 plus T2 total lah 240, 160, 1,600 Newton plus 240. Jadi 1840 lah. So we can make a shear diagram. Okay. So this is our, okay, then we make a shear diagram of this. Shear diagram ni, kalau you tengok since kita adalah only XY plane sajalah. Kan? We only on XY plane. Okay. Boleh nampak live video saya okay? So we are on XY plane. Okay, boleh nampak video saya. Okay, sekarang ni kita on XY plane. So kita punya shaft, okay, ada lagi. Okay, sekarang kita punya okay, so ni kita punya shaft. Kita only on one plane je lah, XY plane only Kita only have SY plane SY plane. Okay, SY plane. So we have our shaft. So we have our shaft like this. Okay, SY plane. So we have our O. We have our B. Only one plane lah, pasal ni tak ada two plane because just SY plane. We have our B and we have our C. Okay, the distance ni kita tahu tadi lah, the distance ni is 250, 450 and 300 kan, 300. Kalau you can see my live video Okay, so kita punya ni 2 kilonewton at O. Okay, we have need this O B, sorry, O A B C Sorry, O, this one is A, B, C. Okay, so bearing O is bearing, C also bearing. At A we have our force is downward or upward? Y direction. Okay. Downward 250 plus, sorry, not 250, 2 kilonewton plus 3 kilonewton. So becomes apa ni? Downward. Berapa value dia? Add up. Berapa value? 2 plus 2.3 kilonewton. Okay. 300 Newton. Okay. 2,300 Newton. 2.3 kilonewton lah. Okay, at B we have all is upward lah. Total at B T1 plus T2. At B we have force berapa tadi? Okay, T1 is 1,600, T2 is 240. So we have 1,840 Newton, or 1.84 kilonewton. Okay. So, okay, sekarang ni, if this is logic is down, so our O logically, our OY here is upward lah. Okay, this is our OY, okay. Our OY. So this one is up, our CY ni is downward, okay. So from here we know lah, ini saya tak payah solve lah, you know moment at O, right kan kelas ini saya want to make to make it short moment at O, then you got your CY so you buat moment at O equal to 0, so you got your CY, the CY, if you look, the CY will be 0.713 kilonewton. So will be CY is 713 Newton downward, memang downward and you buat Fy equal to 0, then you got your punya Oy. Your Oy value is 1173 Newton. Oy is 1173 Newton. So you can solve it lah. Itu cara dia lah. Okay. Okay. Because like this one is just one. Okay. Sorry kalau dia hanging lagi video saya. Hold on je Boleh nampak Okay. Okay, jadi kita make, once kita have the free body diagram, kita buat the shear diagram. The shear diagram. Class, can you watch my thing? Class. We make a shear diagram, Newton. So we know 1173. Okay, raise up 1173 lah. This is 1173. 1173. Then minus 2,300. Minus 2,300. So you got the balance here is negative 1127 Newton. then raise up 1840, it goes up 1840 up until here you got the balance is 713. Must be balance guys, 713, then we get 713 down. So this is our shear diagram. This is our shear diagram. Our shear diagram. Okay, now we go for moment. Okay, we go for moment. Okay, moment Newton millimeter. Okay, moment distance of moment. Okay, is equal to the area. 1173 times 1173 is your level times 250. So you got your moment here is berapa ni? Look on the solution. The moment is 293. So you got here 293 250. Pasal yang solution tu Newton meter. Kisah kita Newton millimeter. 293,250. 1, 2, 3. 293.25. 293.25. Okay. This one, this is your moment at point A lah. So M3 tolak minus M2 equal to negative area. So you got to be careful. So you punya moment is like this, it go to negative side there. And this one value there is actually it's lower than this one. You can get the value. And kemudian you punya moment here, then you go back balance like that. Okay. Actually dia tak given this what is the value here. Hello class, dia tak bagi what is the value. The value here is you can get it value. Actually okay, let's calculate. Let's calculate. Moment 3 minus moment 2, what is the value here? Apa value moment sini? Negative area ni. Ini is 450. Can you calculate for me? M3 minus M2. Class, are you with me or not class? Video saya nampak kan? M3 minus M2. Because this M3, this one is M2. Minus M2 equal to area, right? Area under beaker. Area, so M3 is minus, okay, M2 is 293,250 Newton millimeter equal to area is negative. Area ni berapa? Area ni minus 1125 times 450. Berapa kelas? Tolong saya. Are you with me or not kelas? Hello kelas, berapa? 1127
Negative 507,150.
Berapa tadi? 50 negative 507,150. So M3 become berapa? This one minus ni equal to minus. So M3 will become okay, negative of this. Okay, apa tadi? Negative 507,150. Bring there, we got plus 293,250. So we got here M3 is negative 213,900. 900. So okay, here must be 0 lah. 713 times 300 must be the same thing lah. 713 times 300 213, yeah, with 0. Okay, so the balance M4 minus ni 0. So this 213 negative 213,900 because kita Newton millimeter. Boleh nampak video saya guys? Nanti kan penat saya cakap. Boleh nampak kelas? Hello kelas. This is our moment diagram. Kelas, are you with me? Nampak? Hello kelas. Ya, okay. Kita tahu yang distance kita penting nanti sebab apa nanti? Kita kan, remember kita ada shoulder dengan groove. Actually minimum, okay. Which one is the maximum? B or A or B? Sorry, this A, this B. This negative 213,900. This 293,250. Which one biggest? Class. Which one? A or B? Yeah, A, 293. Even this one negative guys, magnitude, take the magnitude. Take the magnitude, 213. This one a little bit less than 293,250. So A is biggest lah. So our point of considering at area, hold on. Sorry, okay, so since A is bigger than at B, so our point of interest is at area A. At area, okay, be careful. Okay, because I cakap tentang stress concentration factor. Actually, at A betul-betul where you mount your pulley at A, actually betul-betul at A punya level, there is no stress concentration factor because you just mount your pulley. But at little bit offset to the left of A and it's a bit offset to the right of A, we have shoulder. To the left of A, we have groove. Itu yang our point of consideration. Because they have stress concentration. Okay, if you look at the question here, nampak tak? Okay, guys, can you see the question? Class, zoom in. Nampak tak? The question. And let me draw. You punya pulley, let me make it bigger. Your pulley, point A tu, here kan? You mount your pulley there. Ini tadi kita punya moment diagram ya. Macam tu kan? Lepas tu dia turun bawah macam tu. Yang ni tadi value kita 293, betul tak? Okay, 293, 254. Boleh nampak saya punya question yang saya tulis ni. Newton millimeter. Betul tak kelas? Tetapi ada groove tak at this? Betul-betul at my line. Ada groove tak dia? Ada stress concentration tak? Kelas. Are you with me or not? Kelas. Hello kelas. Tak. Nampak tak dia ada offset 20mm, then you have ada radius offset to the right, but you ada. Tapi I mean at here nothing kan, center ni ada line. Tak, you mount your pulley here. Sini yang you mount your pulley. Kelas. You tahu tak pulley punya shape macam ni? Okay, are you watching my video tak? Kelas. Pulley awak mounting betul tak ada plane diameter, tetapi at ni dia offset 20mm to right, kan dia ada shoulder. Itu yang kita kena analyze. Kita kena analyze. To my point tu je lah, simple. I hope you understand. Ada stress concentration but not betul-betul at point A to offset to the right of A at 20mm at the shoulder. You are right. That's what you mean, right? Kan? Ni, at here. So we have 2 points we need to analyze here. At this point, nampak? So you bring to your moment diagram. Tadi moment diagram kita dekat sini at ni. 293250. Ni, you kena calculate apa moment 2 ni. This moment 2, you can analyze. Ni, also this one we have groove. This all. Ini ada nampak tak? Dia cakap all corner fillet radius 2. You mean you have a radius ni. Radius 2mm. Ini radius 2mm. So you have stress concentration there. Also to the left of you, you have groove. You can see groove. You have a notch. Ini yang point weakness. The weakest point actually is not at A tu, yang offset to the left 20mm to the left and also 20mm to the right. Yang ini, this one. Ini yang, this point also you kena bring down to your moment diagram. Yang ni, this point. Okay, what is the moment M1? Tak susah apa benda ni. Ini tak payah, you just pakai theorem Pythagoras ya. Remember tak? You know kan tadi distance you punya ni kan, betul tak kelas? Distance from apa ni? Distance from A to O, betul kan? To O berapa tadi? Distance A to O is 250. This one 250 mm. We know ini value offset dia is 10, betul kan? Offsetnya both is 10. 20 there and 20 here offset. Nampak kan dia bagi distance is 20. So you can get theorem Pythagoras M1 over 250 minus 20 is 230. M1 over 230 equal to 293,250 over 250. So you can get the value of your M1. Also by theorem Pythagoras, tapi theorem Pythagoras for this, you kena tengok moment yang bawah tadi. Moment yang negatif kita tadi, 213. 21390 ni. You kena tengok triangle ni berapa. Ini I hope you understand how you can find M3. So kita kena base this triangle. Understand kalau I'm talking about theorem. So you can get by theorem Pythagoras, and you can get, okay, 293 yang peak moment tadi 250 over the total distance from A to B is 450. It means that, okay, 293 because kita have the peaks here at A, betul-betul point A 293,250 over 450 equal to M3 over minus 20. 450 minus 20 is 430 equal to M2 over 430. So you got your empty value. M2 value. Faham tak kelas habis cakap ni? Simple je ni. Kelas. Hello? Clear tak? So you got the value of M1. So kita kan, our point, kita tak fokus on A tau. Now you focus at groove. M1 at location M2 where it is offset 20 mm. Your shoulder 20 mm to your right. So where you got your M2. And you have 2 point into you can calculate. One is your groove at M1. Okay? M1. So that's how, okay. That's why, okay, itu yang tadi dia cakap. So M1, kalau saya shortcut lah, kalau if you focus on that area, M1 and M2, the value is, if you look on the solution already given, they already done. That's why I study nanti the solution tu. Mana this? Solution M1, okay, if you look on the solution, you can see my kan, solution tu, class. M2 is 270. Can you see that, class? Ini at the shoulder. M1 is 269. So it means that, itulah you punya. So it means that, class, yang tadi, that's why I cakap, you have tadi at, apa, groove kan, situation of your groove. This is your groove, and this is your shoulder. You don't have to draw like that, just to explain to you lah. Yang tadi we have our point A here. This is our point A. So we know that the distance offset everything here is 20 mm kan? Is 20 mm offset to the right, 20 mm to your left. 20 mm from your point A to for your groove. This one for your shoulder. Shoulder we have fillet radius. We have fillet here at shoulder. Fillet. And this one we have also radius. Okay? Okay, class. So that's why you punya moment tadi, your moment diagram tadi, we have peak and peak yang tadi, MA, and it goes down here. Okay, goes down. MA tadi we found out is 293,250 Newton millimeter. This is your moment diagram. So you 20 millimeter to your right, you offset. You use your theorem Pythagoras explain to you. So they found out is 270,170 Newton millimeter. And also yang 20 millimeter offset to the right. Boleh nampak saya video saya, okay. To your left, for your groove location, your M, okay, this is M2. M2, and this one is M1. M1 ni, theorem Pythagoras by distance, pasal ini 20 mm to right, so you can get your M1 is 269,790 Newton millimeter. Clear tak, class? So our point of interest at this location, not at A, offset to the right 20 mm for the shoulder case. Another one for the groove case. We have two cases. One is the groove. Case one for the groove. Case two for the shoulder. So because why? Kita need to find the KF value. Because they have stress concentration factor. Clear Clear So we need to find KF. Understand, class? Boleh buat at both case. Class, are you with me?
Yes, doctor.
So both case. So like this. Okay, now case groove. Okay, you just write groove punya case. At groove, okay, groove punya case, so okay, we have our moment here. Nampak tak? We have our moment. Okay, one more thing, kita kena consider dekat groove tu, I want to tell, okay, groove, do we have bending kan? Pasal since we have moment, at the groove, point here, at the groove here, we have moment. We have moment, so we have bending stress. At the groove, bending stress. Kita punya bending stress at the groove. Okay, sigma bending, ini case at the groove. Sigma bending is 32 moment pi d cube. Okay, for the groove, moment, it mean moment at groove is location, moment is M1. I'm using M1. I'm not using moment at A 290. The one is peak. Where A, we don't have any groove or any shoulder. At A to like plain diameter. Because it's already given in the question also, they give you all the diameter. The diameter of here is 40. This one is 40 diameter. Okay, and this one, or the radius of the groove is 2 mm radius, and also shoulder also 2 mm shoulder. So R is 2. Ini big D is 2. Because if you look at the groove, the groove, if I zoom in the groove, the groove punya case, zoom in like that. Groove macam ni, you have groove. Okay, this is your shaft diameter. Okay, it means that, okay, macam ni. This is your R. R is the notch radius 2 mm. Okay, you punya big D. What you call D? Bigger D. Bigger D is 40. But the smaller D, be careful. the smaller d. Smaller d is 40, deduct both radius. Pasal this will become your small d. D is your smaller d. Your d is, smaller d is 40 minus, because we have two radius, this one is 2 millimeter, so smaller d is 40 minus 4 is 36 millimeter. Clear or not? That is your smaller d. Boleh nampak saya punya tulisan ni? Boleh nampak Kelas, ini. Okay, ini groove punya case. Case 1, kita forget dulu about shoulder. Kita ada dua case. Later kita go shoulder. Kita go groove dulu. Kita kena concentrate. Either this area, that is point of groove ni, will it fail or not? Kita kena find the safety factor. Kita ignorekan A. Because yang we have stress concentration at both. One at the groove, one at the shoulder. Where 20 mm offset to the left, shoulder 20 mm offset to the right. So we need, that's why our point of interest is groove and shoulder. Okay, not A, even A is the most maximal. Tapi this one is likely got bigger juga kan, because 20 mm offset. So our moment, okay, at the groove here, bending stress at the groove, because we have moment, we not use moment at A 293,250, we use moment 1, because moment 1, that's why we saw by theorem, we got that 269,790. So you punya bending at groove, this one at groove. At groove, 32 times you punya moment 1 tu 269,790 over your, okay, pi, which diameter? Diameter cube. Which diameter, guys? Am I using at the groove here 40 or 36? Which diameter? At the groove. Here, this is your groove. Can you see, guys? This is your groove. Groove is tadi 40 minus 4 lah, pasal groove smaller diameter is 36. Smaller diameter is 36. Class, at the groove, which diameter? 40 or 36 here? Hello, class. Yeah, 36. We take the most case lah, the minimum, the minimum, the smaller density, the bigger the stress, the minimum, the worst case is the smaller diameter, right? Not the bigger diameter. Take 36 cube. So we got the value of that one. Okay, the value is we calculate at groove. Okay, hold on, you punya at groove, okay, ni at shoulder. Alright. Alright, okay. At the groove tu, are you with me, class? Okay, saya punya step ni, yang ni dia buat SN dulu. Actually, SN ni you can solve it later lah, tak ada masalah. Ini at the shoulder. Okay, this one you punya case step 3 at the shoulder. I'm talking about the groove dulu. Okay, yang ni at the shoulder. Yang ni saya fokus kat groove dulu. It's the same. Okay, at the groove. Okay, ni at the notch. Ni groove at the notch. Okay, you tengok step 3 yang ni notch Class, are you watching Okay. At the groove tu, you punya, okay, sekarang ni you punya bending stress at groove tu, bending stress at groove 32 moment, D is 36, right? D is 36, so you got 32 moment, okay, pi 36, so you got is 117.80 megapascal. Okay, this one bending stress at the groove, tetapi this bending stress have not multiply KF value yet. Pasal ni bending stress dia tak multiply value of your KF, so this bending stress kena multiply by KF, so you kena multiply your bending stress at groove bending stress 117.80 megapascal, you kena kali dengan KF. KF have to kali your bending stress at your groove punya case. So what is KF? KF equal to 1 plus Q KT minus 1. So what is this Q and KT? Q is the notch sensitivity. KT is static stress concentration factor. So how do we get this Q and KT? Okay, for KT, ni you take note guys. KT is static stress concentration factor. Okay, to get nilai KT, it is not on your chapter 8, it's on your chapter 4 of your textbook. If you can see my Sorry guys, line putus Guys, kau dengar Okay, to get that KT value tu yang class, are you with me? Can you hear me now, class?
Yes, doctor.
Okay. We know that, okay, the equation for my level, KF is fatigue because kita fatigue stress. We need to find KF, then KF to multiply your sigma bending. Axial also, axial we need to find KF axial times your axial stress. Torsion also we have to torsion time axial stress. Okay, KF, okay, you need to find. First we could focus at groove and also our point dulu, bending dulu. Then kemudian we go for axial. But at point A, we have ada torsion tak? Kita consider satu lagi. Okay, we okay, sorry. Okay, our bending stress here. So we have to apply KF bending, right? KF bending. Okay, to find the KF for bending is ready. Okay, take note. Okay, you look at your textbook here. If you look at textbook under static body stress, you go for topic stress, nampak tak? Stress concentration factor. You click at that one. Then it will go to stress concentration. We go to this diagram. Nampak tak diagram class? Figure. Ya, ini you kena highlight juga this thing. Figure apa? What is this? Figure 4.35. Class. Can you see the textbook? To get your KT dulu. Hello class. Okay. Okay, but this one, kalau tengok, this is KT. This one KT for, this is not groove kan. Kita punya focus on groove dulu. This one is shoulder, right? Okay, kita skip. This all shoulder case. Shoulder case. You skip down. Nampak? This one groove. Can you see groove? Ni figure 4.36 is for groove. Nampak? Groove of shaft. Groove. Okay. Groove of shaft ni ada tiga. We have three category here. We have three category. One is case for bending. This moment. Moment mean bending case. We need to find what is the value of KT. And this one for axial stress case, what we need to find what is the value of KT. And this one is torsional stress case. We need to find the value what is the KT. Right. Hold on. Alright. If you look the textbook, we go for bending lah, KF, yang for guru. Do not go for shoulder guys. Shoulder different case. Jangan. The nilai KT that you get, if you go for shoulder case, you want, but your case is groove. You get different value guys. This totally wrong. For groove, go for groove. We are focused at the groove. Okay. Okay, we go for bending first. For bending at the groove, okay. Can you see that this one? Okay, your x-axis is your ratio of R over D. Okay, if you look at my live video, your groove, your R is 2 kan? Your R is 2 millimeter and your R over D, your smaller D is 36, right? So your R over D is berapa? R over D is 2 over 36. Betul tak guys? 2 over 36. Groove, your punya R radius of the groove is stated given is 2 mm and your small diameter is 36. 40 minus 4 lah. So smaller diameter is 36. So it's 2 over 36. Okay, R over D 2 over 36 is 2 over 36. R over D is 0.06. 0.06. 0.06. Okay, another ratio we need to find. Okay, we know that, okay, if you look on your yang figure in your textbook, 0.06, okay, this 0.1, this 0.05, this 0.06 is here. Okay, you draw your line. Okay, you got to use, kalau you pakai e-book ni, you kena print out. Actually, you can use ruler. You cannot, don't use by hand like me. This is not accurate. You have to use ruler. Betul-betul it becomes straight. Guys, are you watching or not, class? Class, are you watching or not? Textbook. Okay, dia kena which one kita need to intersect. Okay, which one? Okay, can you see all this curve on this graph? The curve ni is ratio D over D. Nampak tak? D over D ratio. So in our case, our D over D, big D over D, it means since our big D is 40 for the groove and the smaller D is 36. So D over D is 40 over 36. Okay, 40 over 36, we have 1.11. Okay, 1.1 lah, lebih kurang 1.1. So, you bring your line ni, where is 1.1? Nampak tak guys kelas ni? The second line is 1.1 punya ratio, D over D. All this yang line ni is D over D ratio. Okay, the second line ni, the second line, class, are you watching or not class? The second line is 1.1 kan betul class? Hello class? Okay, so you bring yang tadi ratio tadi 0.06 of your R over D as axis, bring your line up until intersect yang 1.1 lah, 1.1. So you bring to your left that the Y value is your KT below. So it will be ni our bending, your punya bending. For bending is not at the groove, moment, you punya QKT, mana KT dia tak cakap. Okay, KT is, tadi dia cakap KT dia berapa? KT is 2.1 ke? KT is 2.25. Betul lah ni 2.25. Ni saya buat tak accurate. 2. Bring that to D is 1 point. Here is KT is okay, D over D is 1.11, 0.05. 0.05. Ini dia tak accurate ni. Sepatut 0.6 beri untuk moment untuk moment. Hold on jap. Okay. Oh, kacau ni. Hold on jap. Okay, if you look on your textbook, untuk bending, kenapa dia punya figure sepatut dia 2.25 ni 0.5, 2.25. I think something wrong dengan dia punya solution ni. 2 point sepatut 0.06 dengan 1.11 is gonna be 2.2, 2.25. Tapi kalau graph ni moment ni is more like 2.1. I'm not sure about this. Ini is 1.1. What mistake? It is graph ni dengan graph yang ditunjuk graph this one tak sama Hold on jap. 1.1. Kita punya R over D is berapa tu? R over D is 0.06 right? 0.0 R over D is 2 over 36, 0.056 betul lah kan? 0.056 ni here is 0.05 kan? 0.05 you bring up here. Oh saya silap, ini 0.06. Dia 0.056 here, somewhere here. Bring up here, so you bring sampai sini. Sorry, my line is crooked so you got 2.25. Betul lah. 2.25. Understand class? We're talking about class 2.25. Okay, right. Okay. So it means okay, KT, we got KT ini for bending. We go for groove bending. Sir, KT bending is 2.25. Okay. So we put -1. Okay. What is Q? Q is notch sensitivity. Okay. For Q guys, for Q is on your chapter 8 again. Okay. Take note about this. On your chapter 8. On your chapter 8 is about your notch sensitivity. Under notch sensitivity. You go chapter 8. Fatigue punya ni, you go until graph yang ni figure notch sensitivity. Notch sensitivity is here guys no, so this one is surface vector. Notch sensitivity is here figure, hold on. Notch sensitivity is on your mana dia? This one. Ini you kena highlight juga. All you got page 3 or 9. This is notch sensitivity. Okay, notch sensitivity of your case is bending. If you look this, can you see the figure guys? Figure on chapter, figure 8.24 class. Are you with me or not? Okay, notch sensitivity. Okay, since at the groove, the notch radius is 2 millimeter, right? Okay, you don't go in it. Your x-axis is your notch radius because notch is the groove punya notch radius is 2 millimeter. Okay, the bottom one is metric lah, millimeter. So 2 millimeter, so your line will be here. Okay, 2 millimeter. Yang bottom one is, can you see this one? The x-axis 2 millimeter. Okay, 2 mm our notch radius, bring up until where? Mana pula dia nak intersect all the curve ni, which one? To bring to your Y is value of your Q. That is your notch sensitivity. Okay, if you look, nampak there's a lot of curve punya, distribution of curve, they have pattern. This one for 200 BHN kan. This is Brinell hardness. Brinell hardness, this 200 Brinell hardness, this, sorry, 200. Okay, yang in bracket is Brinell hardness. Yang 200 ni is value in SU, This one SU but in KSI. Nampak tak? Yang not in bracket. Bracket you can convert, ultimate strength. SU is ultimate strength of your material. Tapi the value plotted by engineers, because the ASME engineers, Society of Engineers in dulu, dia dah already plot, pakai American always use English unit. They plot the graph distribution all in English unit. So it is 200 KSI. Okay, kita use megapascal or gigapascal. They use KSI, 140 KSI. They already plot the graph. So what means that we need to convert our SUT of our material. Remember our AISI 10445 just now, our material of our shaft kan? AISI 1045 hot roll. We get the SUT in megapascal. We convert to KSI. Ataupun we can get the Brinell hardness, Brinell hardness by using, get the Brinell hardness. Brinell hardness, kalau if you look on the social already given, Brinell hardness is actually, Brinell hardness is your, BHN is your, okay, ni you kena take note guys, ini you kena take note. So Brinell hardness, pasal you need to find your Q. You need to find your Q. Brinell hardness, can you see? Brinell hardness is your SUT over 3.45. Okay, this is standard equation lah. Pasal to get that Q, notch sensitivity, we need Brinell hardness value. So Brinell hardness SUT, your value of SUT divide 3.45, there will be your Brinell hardness. Atau your SUT equal to 3.45 your Brinell hardness. So because we need to find your Brinell hardness of your material is ultimate strength divide by 3.45. That will be your Brinell hardness. So, okay, AISI 1045 hot roll, if you look on your textbook, what is the SUT? Okay, if you look on appendix C, if you look on appendix C, material property AISI 1045, nampak AISI 1045 hot roll, the SUT, not SY, 638. So since your SUT is 638 megapascal ultimate strength, so your BHN equal to 638 over 3.45. So you got your Brinell hardness is, berapa? 638 divide 3.45. So your Brinell hardness is 185 lebih kurang Brinell hardness. So this is a value you find to get your Q's, notch sensitivity. So let's go back for contents chapter 8 tadi, notch sensitivity. Chapter 8, notch sensitivity. Mana tadi? Somewhere around here, somewhere around go here. And chapter 8, a bit up. Where is your notch sensitivity graph tadi? Figure, hold on. What figure is it? Notch sensitivity punya graph tadi. Okay, here. Okay, figure 8.24. Ini you kena highlight you guys, 309. Nanti kena mencari, nanti susah. Okay, kita punya radius is 2 mm. We bring up, okay, we bring up. So until intersect with 185. So where is 185? Nampak tak Brinell hardness? Okay, nampak guys, dia ada dua zone guys. You use this zone, nampak you ada zone, you ada zone 400, 280 BHN, 200 BHN. This is use this value for bending and axial load. Okay, our case just now we consider on bending, so we use this zone. Jangan use the second punya scale. Nampak kita ada dua zone scale. Scale here is for bending and axial. Yang ni scale for torsion. So in our case, our Q, we want our notch sensitive for bending case. So our case is bending, right? So we use the Q ni. Use this scale, use this scale. Not the right punya zone, the left punya scale punya zone. Okay, since our Brinell hardness is 185, so where is line 185 Brinell hardness? Is 200, right? Between 200 and 160. Betul tak guys? So you kena draw, actually you kena print this graph, you cannot do it by like what I'm doing. I just pakai mouse tak boleh. You kena sketch pencil lebih kurang between, because kita 185 something between 160 BN and 200 BHN. So you just put sketch you punya, lakarkan you punya line like like parallel, dia punya flow like that, the same until intersect. Okay, this one intersect this one, it is line for 185 BHN. So you bring to the right, it become, I think it's about 0.8. So okay, let's put on the shoulder. What is our KF for bending? This one shoulder, guys. This one shoulder. I'm talking about groove first. For groove, KF Q, the Q, yeah, 0.8. Betul tak nampak guys? 0.8. So it will be is 0.8. So our Q is 0.8. So just now our KF tadi for bending, KF bending is 1 plus Q KT minus 1. So equal to 1 plus Q is 0.8, okay, times KT just now. KT tadi adalah 2.25 kan, 2.25 minus 1. So we get our KF tadi adalah KF kita adalah 2. KF kita adalah 2. Betul 2.25 minus 1 times 0.8. Sorry. 2.25 minus 1 times 0.8. Okay lah. Betul lah 2 so it's 2. Alright. So it becomes our KF for bending is 2. Kelas. Okay. This KF bending, kelas, are you with me? Boleh bawa kelas. Tak apa. Yijan, you record kan? Yijan. Kelas. Kalau if you understand, you repeat, please see the video. Because this, the step is like this. Actually not difficult, tapi you kena be quite be careful lah about the step. Hold on, video. Sorry, line putus. Sorry guys. Class, can you see live video? Saya nampak Class, are you with me? Sorry, line putus. Okay. So that's why, okay, we have our KF bending equal to 2 kan? KF bending equal to 2. So this KF bending have to multiply your bending stress just now. Your bending stress tadi. Kena multiply by your bending stress. Remember your bending stress at groove just now kan? So your bending stress just now. So you punya bending stress you have to multiply. Okay, bending stress tu have KF times your bending stress just now yang sigma bending lah. Sigma bending. So this your ni kena kali dengan ni. Your bending stress to F KF kali dengan apa tadi yang 32 moment yang before we ni lah. Yang 32 moment 1 over pi d cube. Where we got tadi value ni is 117.80 megapascal. So this is our true case at the groove. Our groove tadi, we consider fatigue stress concentration factor. Clear tak kelas? Okay, tapi memang rumit dia punya, tapi step dia is straightforward like this. Tapi you kena faham lah. Okay, you can study the solution I share you in the link, or you can watch the video. So this KF have to multiply to your yang apa? Nominal punya case when you calculate your bending stress. Okay, so after you so tadi is 117.8 megapascal, so you times by 2, so you got apa tu, sorry, yang tadi 117, actually yang the before multiply by KF is not 117.8 guys. Yang mula tadi, before we multiply by KF is not 117. It's the one after kali KF. Yang tadi is pi, where is pi? calculate for me guys. Yang ni bukan 117.8. Before we calculate, berapa ni? What's the value ya? Kelas. Yang ni before we multiply KF. Before fatigue stress. Berapa value ni?
58.9.
Berapa? Ya, saya silap tadi. Tadi I just direct shortcut see those function. Ini belum lagi. 58.9 megapascal, right? So 58.9 kali K, since your KF is 2, right? Kali 2 lah. 58.9 kan? Itu 58.9 times 2, yalah you got 117.8. Okay? So yang tadi already yang ni, yang 17.8 tadi tu yang ni. So you got your value is 117.8 megapascal. Okay kelas understand okay, memang leceh sikit okay. Tapi exam question is not this detail lah je, bagi simple. Tapi ini assignment better you study this thing. I think kalau you faham this procedure, yang lain assignment should be no problem for sure. Okay, this only on bow bending. Kita still on groove, groove case. Tapi remember groove we have, nampak tak groove kan? Remember we have axial force class. We have axial force external, betul tak class? Hello class. Kan in the question kan? In the question we have external force 2 kilonewton or 2000 newton. So along OABC we have axial stress. It means we also have axial stress at the groove. At the groove we also have axial stress. Okay, we go for axial stress. Okay, now for axial stress. Okay class. Okay, remember this is your groove punya case. Groove punya case, this is your groove. I make it bigger. This is your groove punya case. Okay, then only kita focus shoulder lah groove. Okay, we know tadi ini radius dia 2 kan? The notch radius is 2. The bigger radius is 40, and the smaller d is sorry class, dia putus-putus line. Okay, sekarang tadi kita, okay guys, tadi where do I stop tadi? Tadi yang okay, we have just now our bending tadi, bending case at the groove. Guys, can you hear me now, class? Okay, just now bending we multiply by KF, we want 117.8 lah. Okay, bending. Okay, now we gonna focus at axial stress. Remember, we have axial stress also kan? Then the question here, we have axial load kan? We have axial load here. Okay, we have axial load. We have 2000 Newton pulling the shaft along OABC. We have axial stress. Okay, it means we have axial stress. Okay, if you link my video for axial stress. Tadi bending sekarang ni axial stress. Okay, axial stress. Okay, so it means you punya what is sigma axial? Sigma axial yang nominal without multiply by KF. Nanti we have to multiply KF axial, fatigue stress concentration factor based on axial. Okay, sigma axial is berapa? Shortcut formula for solid shaft 4F over pi d square. Actually it's force cross section area. Cross section area will be your diameter 36 guys, and not diameter 40, because the worst case is the smallest diameter. That is the biggest axial stress there. So here at the cross section 36. So for F, so we know that the force is berapa tadi? 2000 Newton, 2 kilonewton. So yang ni adalah 2000 Newton over pi 36 square. So berapa ni megapascal? Berapa kelas? Megapascal dia berapa? Untuk axial load 1.96, small kan, biasa axial 96 megapascal, right? Okay, remember sigma axial kena times KF axial. Tadi KF bending, you have to times multiply KF axial. Okay, KF axial pula, KF axial sama equation juga 1 plus Q tadi no sensitivity, right? Remember bending and axial same graph. Same value pasal bending, I explain to you. And KT, this one KT axial, this is not KT based on bending. KT minus 1. Just now yang KT that we find yang tadi, KT based on bending 2.25. But now we need to see figure balik on chapter 4 tu. KT based on axial punya case. Okay, what is, we go back to chapter sorry, line putus lagi kelas. Okay, where was I tadi? Okay, sekarang just now on axial If you look my video, so we calculate. Yang ni tadi saya up until here betul kan? Yang ni tadi, I explain to you. Before line putus, kelas. Kan? I already explain here kan? Okay, now this axial yang, sigma axial yang 1.96 is nominal without kali KF. You have to multiply KF to get the actual value because stress concentration factor. So KF axial is 1 plus Q, no sensitivity will be the same value as bending is now. But your KT axial 2 is different. KT axial 2 you go on figure 4 balik tadi, page 150 ni. Okay, ni, this one grow, just now we take the first graph. Just now we take the first graph based on bending. No, the second graph, the second one. This one apa tak? Axial force, P. Ni gauge for axial. So the same method. What is R over D tadi? R over D tadi is apa? R over D is 1 point tadi, 0.0 is the same thing lah. R over D kita punya R over D is 0.06. Okay, 0.03. You can see my textbook guys, class. R over D is 0.056 0.056. Class, are you watching the figure ni? 0.056 somewhere here. Intersect what? D over D berapa? 1.11. 1.11 mana? Ni lah, this one 1.1. 1.11 lebih kurang sikit. Ataupun you draw up as, I think 1.11 is 1.1 lah. You draw up ni, okay, you bring that. So you punya KT for axial is 2.3 kan? 2.3. Let's show on the show. What's the value of KT? 2.2 juga. Apa salah tak sama? 2. Hold on. 2. This one for axial, right? Axial, this one also for axial. Our R over D is 0.056. 0.56 over, then we bring it here 2.2. Tadi just now bending and bending 2.25. I think, I don't know, maybe solution to 0. Kenapa tak sama guys? Bila ni 0.0, apa yang beza graf dengan dia? Sama kan? 0. Like the graph tu like kind of different. Maybe they look from the 1.1, betul lah 1.1. Intersect here, they bring ni 2.2. Kenapa my intersect? Maybe my line is crooked or not? It's 1.1. Bring is here is 2.3. Betul tak kelas? Can you see that they're different class? Hello, are you with me or not? Kelas? Korang ni faham ke apa saya cerita ni? Okay, apa ni, kalau if mine ini is 2.3 kan, tetapi on the solution given ni, pasal graph dia lain tau. Maybe tahu lah, borders on graph, dia 0.056 is R over D. And dia punya D over D is apa? 1.11. And D is ratio D, bigger diameter over smaller diameter. You get, memang tahu lah 2.2, this graph. But this graph, what mistake? This is groove, right? This is groove. My graph here, this is groove. Apa different dia? Apa mistake do I made? No, this is not. This one plate lain. Plate is not sharp. This is the consideration. Okay, tak apa, never mind. Okay, let's say kita go for the solution given tu. Okay, actually kalau axial 2.3, tak apalah. Okay, so you get dia from dia punya graph ni, from your solution ni. Dia punya ni, the got is 0.056, bring the got 2.2. Nampak tak kelas So KT is 2.2. Do you understand or not? Kelas. Axial Axial go for axial. So kelas, so you punya KT tu is 2.2. Okay, what about Q? Since Q also Q axial, tapi remember our notch sensitivity for kalau if you look on the textbook for the go back to for contents chapter 8 balik, if you go for chapter 8 again under notch sensitivities, the notch, this one figure 8.24, the axial and bending we use the same use this value for bending and axial, so it's the same value of your Q tadi lah, so we will use the same Q. We will use the same Q, whereas our Q is berapa tadi? Our Q is tadi berapa tu? Q is 0.8. Tadi Q is 0.8. I tak mention tadi. Q is 0.8 for your graph. Q is 0.8 from here. We use the same. Pasal this one use this zone, this zone of scale for bending and axial. So we intersect dengan our BHN tadi. Berapa tadi BHN? Our BHN yang tadi. Berapa BHN tadi kita calculate? 3.45 tadi. So we get our so our Q tadi Q is 0.8. This one for bending kan. You can still watching. Takut line tak putus boleh. Saya pun heran. Class, can you hear me class? Boleh Q is the same. Pasal bending axial Q is the same. So your Q ni is still 0.8 lah. Q0. So your KF equal to 0.8, 2.2 minus 1. So your KF is, kalau if you look on the solution, your KF to the give is, your KF is apa? So your KF for axial punya load, your KF is 1.96 Okay, 1 plus ni 0.8 in bracket 2.2 minus 1, so 0. KF is 1.96. So KF is 1.96. Okay, KF is 1.96 pasal 1.96 is nominal without stress concentration factor. So you punya sigma axial is KF kali tadi for F yang tadi you calculate 1.96 for F by D square. So it become 1.96 times 1.96 lah. The same value. To 1.96 times 1.96. So the value is 3.85. So it's 3.85 megapascal for your axial. Okay. Axial to you is 3.85 megapascal. Okay. Alright. At the groove. Okay. Understand class The one you focus at the groove. Okay. Now, if you look sekarang class, at the point A ni, do we have torsion tak? At the groove. Ada torsion happen at the class. Look carefully. Class. Hello class, are you with me or not? Class, can you hear me? Okay. When you draw torsion diagram, okay, remember you buat torsion diagram. Torsion diagram from where to where? Class, where's your torsion diagram? Bila you buat torsion diagram, kan you buat moment diagram, you buat torsion. Torsion start from point A sampai point B. Betul tak? Remember your torsion and X direction. Torsion like this. Pasal this one torsion, it goes for positive, something like that, go positive, and here it go back, cancel out, 0. This is torsion. Betul tak? Your groove ni ada torsion tak? Is 20 mm offset to the left. Ada torsion tak ada groove? No, yes, you are right. No torsion because the groove, torsion only starting at A until B it cancel out. Torsion only happen from A to B. Before A, no torsion. So the groove is before A. But the shoulder have, the shoulder have. The shoulder have. Okay. Now sekarang ni, okay, since at A ni, there is no torsion, be careful. At A, there is no torsion. Only we have axial stress here because axial stress, you have external load. Axial stress along OABC, we have axial stress. because external load 2000 Newton. And also bending, just now we have bending dekat groove because based on moment tadi kan, moment peak at A, the moment at M1 yang you calculate by theorem Pythagoras, you can get your M1 value already ni. That one too. But this one we have only, so it means that kat groove punya point, we only have bending and only axial. Okay, that's why in this solution dia tak ada. Kalau you calculate torsion stress, you wasting your time. Totally wrong. You punya answer will be wrong. So only at point groove tu, we don't have torsion. We only have axial and bending only. We only have at notches at groove. We only have bending and axial. Okay. Okay, now tadi as I explained to you, kita have sigma axial is 3.85 after we multiply by Kf axial. And apa tadi? Bending stress is bending stress just now is bending stress after we multiply by Kf bending is 117.8. Okay, tengok kelas Okay, one more thing. Okay, now it means at groove A tu we have only axial and bending. We don't have torsion. We don't have torsion. Okay. Okay, we know the equation that if you look at the equation, remember the equation that in your textbook when we combine stress by axial, okay, in your textbook on chapter 8 on this page kan, when you combine stress yang apa tadi? Combine kan this equation. Apa tak on page ni? Ini kena take note yang combine. Sigma EA kan, remember your sigma EA. Okay, sigma E alternate equal to sigma alternate square plus 3 tau alternate square. Okay? Because we sekarang ni kita fokus dekat notch at groove. Notch groove. Groove is groove. We don't have torsion. Okay? We don't have torsion. Okay, we need to calculate. Okay, since our element at point yang saya cakap tadi, where you punya at notch ni, you punya point kat sini. Element at you punya notch, I draw it again. You punya element at you punya notch ni. Okay, sorry guys, I've got line, boleh nampak saya punya. Hold on jap. Hold on guys, sekejap. Kelas tunggu je soalnya webcam saya ni. Hold on jap. Okay, boleh nampak my video kelas. Saya tadi my phone tadi dah ni, I'm using the second phone ni for my webcam. Can you hear me or not? Okay, video dia fokus tak? Boleh Okay. Jelas tak? I'm using different phone now. Yang tadi cause problem, that's why. Okay, it means at point A tadi, groove tadi, kita have only bending and axial. So it means that at our groove just now, our groove is like this. Okay. Okay, sekarang ni shoulder tu lain cerita lah. I hope shoulder you see the solution yang I share you the internet. I hope by me explaining you at the groove, you know cara dia macam mana Shoulder tu I think I don't have time to explain. I hope you understand. But at shoulder we have both. We have axial, we have bending, we have torsion. Remember, KF for bending, go for KF bending like I explained just now. But in your case tadi shoulder. Okay, hold on. Kita go for groove. Itu later on. Okay, for the groove, Imin, kita punya case here. So we already have KF axial, kita dah multiply our axial stress with KF axial. Our bending have multiplied with our KF bending. So we have, okay. So our element here, so mean we only have element here is here. Kita punya consider sini. So element at that point tu, kita only have, so since we don't have torsion, so our sigma axial we have, and we have sigma bending. Nampak tak? This one already all kali KF axial kan? This one bending kali KF bending just now. Okay, KF bending. So we add it up together. Okay, so so your element two only have one direction. Okay. Okay, tapi before that, okay, remember the equation. We need to find sigma EA. We need to find sigma EA. Sigma EA, equation sigma equivalent, because we need consider kita using the ET lah. Sigma E alternate equal to sigma alternate square plus 3 tau alternate square. Okay, in our case, okay, I want you to consider this thing. This is your shaft. This is your shaft OABC just now. Your shaft OABC, where you have this one, you have pulley, and you have axial load just now, F 2000 Newton, and the shaft is rotating. Remember, guys, the shaft is rotating. The shaft is rotating. Okay, the shaft is rotating. Kalau kita plot bending, okay, bending through times, okay, this is sigma bending through time, the shaft is rotating. Let's say element here. Can you see my video? Tak nampak? Element here. The shaft is rotating. Element in terms of bending stress, how is the stress distribution with time? How we plot it? It is completely reverse. Betul tak, kelas? Bending, sigma bending stress. Class, are you with me or not? Are you with me? Bending stress through time, dia completely reverse. Betul tak? You punya element at groove here. Hello, class. The shaft is rotating. Class, clear or not? Class, can you hear me or not? Are you with me? Okay. Okay. Because we need to find sigma EA, right? Sigma E is combination distortion trajectory. We have sigma amplitude square plus tau 3 tau amplitude square. Okay. Of course, tau, this one will become 0 because since we at groove, we don't have torsional stress. We don't have torsional stress. But we have sigma, right? Sigma we have sigma case for axial and sigma case for bending. Sigma case for bending. Okay. Okay, in our case here, for bending stress, because bending stress, it means your element, the shaft is rotating. Your element to bending to will face dia punya plot of sine bending through times. It become like sine wave completely reverse. Betul tak? Remember I cakap, kalau you punya shaft is rotating, your element tu is up on the top, shaft is rotating up and rotating. So you punya element at the top, and you punya element at point, you punya interest at the groove tadi, at notch tu, will face tension, compression, stress, but it remain the same value. So you punya only bending, only we have sigma amplitude. What is your sigma amplitude? Sigma amplitude that you calculate yesterday, yang times the KF bending, yang 117.8 megapascal. That is your punya amplitude. Okay, so this is your sigma amplitude bending where it is 117.8 megapascal. You times with KF bending. Okay, that is bending. Okay, remember at the notch also we have axial. Sigma axial. What about axial stress plot through times in this case? Okay, this is your shaft. This is your notch. You have axial force. Now you have axial stress. You have force here. You know just now sigma axial we calculate for F over pi d square times KF axial. That is our, then the value just now we calculate is berapa tadi? KF axial is 3.85 megapascal. KF axial 3. We time by KF axial. So our axial stress 3.85 megapascal. That 3.85 megapascal plot to time axial stress, will it be sine wave or is it a straight line?
Straight line.
Yes, you are right. Very good. Credit to you. Very good. Straight line. Same like, but since at that point notch, we don't have torsion. Torsion don't care. Torsion will become 0. It's a straight line. Axial stress, even the shaft is rotating. Your axial stress is direction on X. At any element, you rotate along the circumference, the axial stress remain the same. It does not facing tension compression. It's because it is axial stress. It remain in tension. Understand? Clear tak, class? So, sigma axial stress, do they have alternate? No. Alternate untuk axial is 0. Sigma A is 0. Untuk axial, sigma A is 0. But axial, do they have mean? Okay, untuk bending, the mean is 0. Since the positive and negative is the same value, because means is the average. The mean untuk 0 for the bending. But for axial, The stress through time, it become a straight line. That axial to just now, we calculate yang kali dengan KF is 3 point, this one, sigma. They have sigma mean lah. What I mean, sigma amplitude, we don't have amplitude. Amplitude is, you have sine wave, you have amplitude. But axial, just a straight line, no amplitude. Mean amplitude is zero, straight line. It remain constant through times because axial stress remain constant. Even your element is rotating along the circle or shaft. Shaft is rotating. But the stress remain the same. Uniformly, it remain axial stress along X. It does not change. But bending, yes. Bending, yes. Your element will go up, will go down, will go up, go down, go up. Because when go up, it tension, go down, compression. Tension, stress, bend, compression, compression. Tension, compression. So that's why the plot is sine wave and the mean is zero. And you have the amplitude. Amplitude is 117.8, where that one you kali dengan KF. And because stress, fatigue stress. And axial, okay, axial along, even the shaft is rotating, the axial stress along the shaft remain constant. Same like torsional stress. Remember, torsional, if you want to go for the torsional direction too, is remain the same. Tetapi at the groove, at the notch, we don't have torsion. Remember, torsion between only A and B. Before A, we don't have. Since the groove is before A, 20 millimeter offset to the left, before A. So it means axial stress is mean. We only have mean. We don't have amplitude. We don't have alternate. We only have mean. Mean yang just now we calculate 3.85. We calculate 3.85. So sini yang Siman mean 3.85 megapascal. We multiply by KF axial. So we have only this one. Okay, since our equation, hold on guys, sikit lagi. I don't want to go for shoulder. Shoulder you study by yourself. I hope my ni saya explain to you about yang itu saja. You have you understand. Then you kena tengok solution tu you study untuk case. Mana equation tadi? So the equation that we have, okay, sekarang ni sigma EA equal to now, because EA we need to find combination lah, equivalent stress alternate equal to sigma alternate square plus 3 tau alternate square. Okay, since we don't have any solution, of course this one is zero. But what about this sigma? We have two case, right? What do we have sigma alternate here? Apa yang ada alternate? Axial and bending. Which one ada alternate? Class. Nampak tak my writing ni? Which one ada alternate? Bending ke ni? Class, are you with me?
Bending.
Yes, you are right. Bending saja alternate. Sigma bending ni. So, clear tak class? Sigma alternate ni. Only bending. Bending saja we have. We don't have, for axial we don't have. So, we only use 117.8. So, 117.8 square plus, ni zero lah. Zero. So, we got, elastic sigma EA is the same as 117.8 because we square root of that square. Okay, sigma EA is 117.8 megapascal. Okay, now the equation for sigma EM. Okay, sigma EM mean. Because you need to find the equation mean equal to sigma mean over 2 plus square root tau mean square plus sigma mean over 2 square. Okay, now our case. Do we have sigma mean? Look at this one tadi. Do you have sigma mean tak? Nampak tak saya punya video ni? Biarlah, mungkin kau tak nampak video saya ni tak fokus ya. Do you have sigma mean, class? Class. This question. Nampak tak? Sigma mean. Ada sigma mean tak? Tadi bending. Bending ada mean tak? Mean zero kan? Class. Ya. Tapi axial ada mean tak? Axial ada mean tak? Pasal notch tu ada axial kan? Only notch tu tak ada torsion. Notch tu we have bending and axial. Ada mean tak? Ada kan? Axial mean. Plus. Kan axial we have mean. Mean. This mean. Purata. But we don't have axial stress. See, dia tak ada sine wave. Just a straight line. If it is a straight line, constant, we have mean. We don't have alternate. Alternate is zero. If it is completely reverse, mean is zero. We have alternate. We have amplitude. Faham? Okay, so this is sigma mean kan? So we use sigma mean axial. Because sigma axial is sigma mean. Faham class? Do you understand that? Sigma mean is your sigma axial. Axial stress we have mean. We don't have alternate. Clear or not class?
Yes, Doctor.
Okay, so we use 3.85. So 3.85. Okay, this is axial. Okay, 3.85 over 2 plus. Okay, we don't have tau, right? We don't have any torsional stress. Betul tak class? Class? Zero kan? no tau. We don't have torsional stress at the notch, at the groove. Okay, plus, okay, this one is 0. Okay, we have sigma min tadi adalah axial lah just now kan. Sigma min yang 3.85 over 2. Do not, because nanti guys, you substitute value yang bending, totally wrong guys. Bending, we don't, in this case, bending completely reverse. We don't have min. Min for bending is 0. We use axial. Katakan your case, you don't have axial, yes, totally 0 you punya min. Okay, itu different case. Tapi yang our case, we have axial stress and external load. So the mean is, because axial stress through time, we have mean. Mean is 3.85. When you kali by Kf axial to your nominal axial stress. Okay, 3.85 square. So we get our sigma EM. Okay, if you look at the solution, ya, tadi apa dia cakap apa? The solution, okay, you put the value 3.85 lah, betul lah, 3.85 plus 2, ini square root 3.85, 2 plus 2, 3.85 lah. Okay class, understand tak? Same thing, okay? Hello class. This is your sigma EM. This one is your sigma EA 117.8. Class, hello class? Clear? Okay, jadi that's what we got. Okay, our sigma equivalent alternate or amplitude is 117.8. And our sigma EM is 3.85 megapascal. Okay, so you straight away calculate the safety factor. So safety factor, okay, sigma EA over SN plus sigma EM over SUT equal to safety factor Goodman line lah. Okay, Goodman line. Okay, panjang juga cerita ni. Tak apalah, ini I hope you learn lah. Tapi kalau for your test tak ada this long lah, dia bagi you little bit simple lah, simpler Okay, sigma EA already class, are you with me? Sigma EA already known, sigma EM already known, SN tadi kita belum habiskan, SUT kita tahu. Berapa SUT tadi just now? Tadi we just find out our SUT berapa? SUT berapa? 1045 AISI 145 hot roll is SUT is 638. Ini 638 megapascal. Ini known. Ini sigma EM 3.85, sigma EA 117.8. The only thing is SN saja. Okay, why is SN? SN is your endurance limit. Actually SN you can calculate earlier just now, tapi depend on your approach lah. Yang ni I solve ini dulu, then only SN. So, okay, clear you me, you see my video. SN equal to CL, CG, CS, CT, CR, SN prime. Okay, we know SN prime is 0.5 SUT for steel lah. This is only value for steel lah. 0.5 of your 638. So it will become berapa? Calculate, saya punya calculator saya ada, phone saya guna untuk webcam lah. Calculate for me.
319, Doctor.
So it's 3, ini S prime 319 megapascal. Okay, what about load factor? Okay, tengok load factor guys axial load compare dengan bending load. Mana kita punya calculate tadi? Kita punya bending is 117.8 megapascal. What is our axial load? Axial load kita tadi kali dengan KF axial berapa? Only berapa tadi? Kita calculate axial load kita tadi berapa? Axial is 3.85 kan? 3.85 but bending is much bigger. Bending is 1. You mean bending govern. Bending govern. So we need to find load factor. Where is load factor? On your textbook. Okay, look on your textbook tadi table 81 right for ni. Nampak tak load factor? Load factor bending. Okay, sometimes student will ask, which one do I to use, sir? Is it bending? We have axial, we have torsion. Because bending is more bigger than axial, we go for 1. Can you see my textbook, guys? 1, So your CL is 1, okay? Your CG, size factor, gradient factor, okay? The gradient factor is the shaft diameter. The shaft diameter, okay? The shaft diameter for your case, okay? You punya case, shaft diameter you berapa diameter? Which diameter do you use? Class. Can you see the question? I make it bigger. Nampak tak? Kita punya point tadi for the groove here kan? Shaft diameter kita berapa? 36 or 40? You can go for 40 or 36 pun boleh. Tapi point kita ni 36 lah, kan? Kelas. Shaft diameter berapa? 36. Okay, kalau you go for 40 pun mungkin nasib boleh lah. Pasal if you look at 36, it should be 36. 36 falling between what category? 36 is between 10 to 50. So value 0.9. Betul tak? So kita tengok solution. Kita punya SN tadi yang dia calculate. Actually SN dia already calculate at the beginning. CG supposed to be 0.9. Mana dia? CG, betul. Nampak tak guys? CG 0.9 So CG kita 0.9. Okay, kita why 0.9? I cakap tadi because kita use 36 mm between 10 mm to 50. Not yang atas, not 1. 0.9 because kita based on bending 0.9. Not axial guys, go for column bending. Okay, what about surface factor? Surface factor CS guys, sikit lagi boleh tak little bit more. Surface factor. Okay, surface factor is the surface factor figure. Where is surface factor? Is this one. Surface factor is figure 8.13. Okay, they mention in the question is that they mention that the shaft ni kalau dia cakap is polish, mirror polish, be careful. Nampak tak? They mention had been machine, only machine. Nampak? Just machine because shaft always be lathe machine. So lathe machine it means that kita use graph machine. Okay, now we draw to get our CS. Where is CS? Our SUT. Remember our SUT is 638 megapascal. So 638 megapascal will be 0.638 somewhere. Ini because it is 0.7. This is 0.7. 0.638 will be somewhere around here. So you just use by pembaris guys. Jangan pakai macam ni. Use pembaris until you bring up intersect. Nampak tak? This is line machine. Normally kalau machine memang shaft always machine. Unless it is machine, the shaft is grounded. The shaft is mirror polish. Be careful. You have to use ground here. Mirror polish just a straight line. Bring it up there. It's always 1. Okay, for machine you just bring 0.638. Nampak tak? There is 1 gigapascal. 0.638 gigapascal until intersect here. Bring it there. So you punya answer supposed to be, you punya solution, you mentioned that, betul lah, 0.CS, mana CS 0.76, betul tak? 0.76, betul lah 0.76 Claire, 0.76, so 0.76, so it means, itu punya ni is, CS is 0.76, okay, what about CT, temperature? Okay, in the question mentioned that, the temperature is 200 degrees Celsius. 200 degrees Celsius convert to Fahrenheit. So only berapa? Berapa convert? Convertkan Celsius to Fahrenheit. Cepat sikit, tolong saya. Phone saya guna untuk webcam, saya tak boleh tengok. Pakai browser pun boleh. 200 degrees Celsius convert to Fahrenheit. What? Berapa? Tambah 273 lah, saya pun lupa dia question. Plus 273, right? 473, yes, 473. So you look on this one, on your knees, for your temperature CT, kalau berapa tadi? 873 Sorry. 473. 473 is less than, ada? Tak, bukan. Dia orang Kelvin. Check to, tak, search Google, 200 degree Fahrenheit Celsius, convert to Fahrenheit, berapa value? I'm just explaining again. 392 Fahrenheit, okay? Okay, 392 Fahrenheit, still under less than 140 Fahrenheit lah, so it will become 1, okay? So you tengok your solution, betul lah dia buat C, temperature is 1, less than 140. Okay, so your CT is 1. Okay, the next one, CT dah, CL, CG, CS, CT, last is reliability. What is given in the question? Reliability berapa persen? 90%, nampak in the question, 90%. So in your textbook for CR, 90% reliability. Nampak, you go for column bending guys, pasal kita bending yang govern, 0.987. So in solution mention lah 0.987 relative. Okay, so your CR is 0.897, 0.897 because 90% reliability. So you just put into equation lah. So your SN equal to 1 kali 0.9 kali 0.76 kali 1 and kali 0.897 kali your SN prime. SN prime is 319 megapascal. So you got you punya SN dalam solution juga SE dash SN is 195.72. Okay, straight away kita calculate the safety factor lah. Kita calculate the safety factor. So we already get our endurance limit. So the safety factor tadi apa safety factor tadi apa? Sigma EA over Sn plus, can you see my live video? Your sigma E mean over SUT equal to your safety factor. So what is our sigma EA tadi? Sigma EA kita berapa? What is our sigma EA just now? Sigma EA is apa? Sigma EA is 117.8 over Sn is 195.72 plus sigma EM kita mana tadi kertas semua dah. Okay. Sigma EA 117.8 kan. Sigma EM is so you got the safety factor lah last kali safety factor for the groove only Okay, you kena calculate also for Langer kita apa ni hold on tu. Ini for sigma EA, okay, sigma EM is 3.85 over SUT is 638 equal to your over one safety factor. Okay, so the safety factor you got is your safety factor based on Goodman. NG ni Goodman ini Goodman ini adalah Goodman punya Goodman. Pasal I remember as I told you, yielding also kita kena consider. So safety factor you got is 2.294. So safe lah. Base argument memang this one infinite life. Kalau more than one, it means the shaft, the system will save infinite life based on fatigue analysis. Okay, remember I cakap you yielding, because yielding. Because why? You punya SN curve tu, you punya sigma mean and your sigma amplitude, since amplitude V is SN and this one is SUT. Goodman line is here, SN and SUT. Anything above fail, anything below ni. Tetapi SY here, SY and SY. Be careful about this zone, SY, because reading will happen. Maybe you punya point lies in this zone. This zone yang point consider you kena tengok. Kalau you punya point even in Goodman is safe, tetapi on yielding dia dah above, dia fail. Okay, you don't have to draw this graph actually, but you can use the simple equation jugalah. Okay, get also for Langer. Langer is for leading. Just now Goodman. Langer punya equation sigma EA over SY plus sigma EM over SY equal to safety factor. Ini Langer. Ini tadi NG ni Goodman you understand? Ini Langer punya safety factor. Pun you kena check juga. Guys, are you with me guys? Sikit lagi. What is SY? SY berapa? Tadi kita get SUT. SY for ni berapa kelas? AISI, kita go back textbook. You punya appendix. Hold on your appendix C 1045. Guys, are you with me kelas? Boleh lagi sikit lagi? Hello kelas? Boleh okay. Ijan you record kan, tapi you edit sikit lah bagi diorang yang lain-lain ni boleh refer balik Ijan banyak jasa awak ni. Okay. Alright, 638 for nampak SY, do not use ni this is SUT. For Langer tu you use SY value 414 nampak Kelas, are you with me kelas? This textbook nampak 414 megapascal, 41045 or kelas 414 megapascal. Kelas, hello kelas, are you with me? Right. So sigma EA tadi 117.8 over tadi 414 plus 3.85 over 414 because your SY tadi SY is 414 megapascal equal to 1 over safety factor Langer. So safety factor Langer tu dia dapat is also safe. And safety factor Langer ni yielding 4.1. So you kena check both guys. You make sure kalau you buat fatigue analysis, calculate both. Satu for Goodman, satu for ni. Make sure that both is above 1. It means the shaft is selamat untuk case groove saja. Only bau groove. Shoulder tu you tengok solution. Boleh kelas? Okay, boleh tak? Boleh hello, you faham yang ni? Ni ada cerita shoulder tadi ni. Shoulder ni saya tak nak explain to you lah. Remember, basically kita have shoulder punya case. Tadi the same method, tapi kita go for shoulder. I don't want to explain to you. You read the solution. Okay, you look on the solution that I share tu. Shoulder tadi, remember tadi. Kita tadi we have groove. Guys, hold on sikit je. Okay, ni you punya groove. Tadi groove kita dah fokus. Pasal kita ada 2 point of consideration that we need to consider. Remember yang tadi, kita ada shoulder. Shoulder ni be careful guys. Okay, ni you punya point A, you punya graph. Yang ini maximum tadi, 29 something kan. Be careful. Yang tadi kita already find this M1 tadi already done. Ni you kena, because this is 20 mm D is 20 mm here and 20 mm there. Yang ini M2 pula, theorem Pythagoras, you can get your M2. Tadi kita already calculate right tadi kan, M2 kan. You tengok solution dia bagi. M2 is, you dah correct, theorem Pythagoras 270. M2 is 270, 170. Approach is the same macam tadi. Okay, you kali dengan, tapi be careful guys. You just mind, you punya case, your KT, remember, you punya bending stress times KF bending. KF bending 1 plus Q, Q bending plus KT bending. KT bending, I just want to highlight to you guys. KT bending on chapter 4 tadi again. Okay, chapter 4 stress concentration factor ni. You jangan guna notch, you guna you guna yang this figure. You guna, nampak tadi guys, are you watching the textbook ni? Nampak, this is notch kan? This is notch. Tadi kita punya case at point tadi notch. Sekarang ni shoulder. This is shoulder. Nampak tak? D over D and R over D. Okay, look at my live video ni. You punya case like this. You punya case macam ni, you punya ni. Macam itulah you punya ni. So this is your big D. Big D kalau in your equation, you punya soalan, you punya solution, you punya diagram, big D is 60. D is 60. The small d is 40. Small d is 40. And the R, the radius, the R is 2. Because dia cakap fillet radius is 2. So your approach is the same. So you use that apa? In your textbook tu. So in your textbook tu, you ambil the ratio R over D, D over D. Ni untuk shoulder. Nampak? Untuk shoulder. So like if you look at my live video, you ambil R over D is 2 over 40. Okay, is 2 over 40. Okay, tadi 2 over 36 kan untuk groove. Yang ni 2 over 40. Yang punya big D over D is 60 over 40. The same approach you pakai to get untuk your bending. Satu untuk your axial. Remember, untuk for your shoulder you ada 3 case. Why? You also have torsion. At the point yang ni, this one you have both. Pasal sini we have bending because our point A here, remember our torsion diagram. After A and before B, we have torsion. It means our shoulder is after A, we have torsion. But the groove is before A, we don't have torsion. So at this one, ini itulah, you kena buat both. You have apa tu? You have bending, you have torsion, and you have axial. Tapi remember, you punya bending, bending plot through time at shoulder, bending of course normally, bending is completely reverse. You have bending, mesti you ada amplitude. Untuk bending, sigma bending, yes. Untuk, as mentioned to you, sigma axial plot through time remain constant. You only have sigma mean. So sigma amplitude is 0. For bending, sigma mean is 0. What about torsion? Torsion, yes. Torsion, yeah, you at shoulder you have torsion. Torsion through times, torsion also straight line. Remain the same. And I'm talking about shoulder because shoulder you have torsion. You have both. You have bending, you have axial, and you have torsion. But shoulder also you have torsion. You have tau mean saja, where your tau amplitude is 0. Same like axial. Ini you can consider. Okay, kalau you tak faham pasal you look on the solution that I already share ni. Okay, tengok the way how the solution explain to you lah. I hope you understand. Ni the solution just now ini. Okay, for tu dia ada explain. You tengok yang the case for shoulder. Okay, jadi ini panjang sikit lah cerita dia. You have shoulder, tadi kita just solve for groove lah, for notch. Okay, kelas, saya stop kat sini. Alright, we go for attendance. Lepas raya. I'm not sure. Yeah, lepas raya. Kalau you look on your, ni, you punya course plan ni, CI kan ada mention ni kan ada tulis situ you punya lecture plan ni. Kalau you tengok your lecture plan, yeah, okay, itu penyelaras, itu koordinator yang buat. Yeah. I pun heard dalam through lecturer punya WhatsApp group, they mention they want to change to lepas raya. Do not worry lah, not before raya, lepas raya. Tapi soon lepas raya lah. Yeah, I understand. Apa tu, if you look on the, if I share you the course, kita punya course outline ni, kita punya schedule kita ni, boleh nampak tak sini? You boleh nampak tak ni, kita punya course lecture plan? Test 1 ni, kalau tengok lecture plan, test 1 ni is on the week 8, 8-5 ni, standby lah 8-5 after raya tu. It could be this. The earliest is at 5. I think it could be later, after 8.5. Tapi standby lah 8.5 after raya, test 1. Itu yang I refer to this. Okay, it should be after raya, not before raya. Before raya, that's why I heard the coordinator want to set it maybe at 8 May. Just standby lah. Or maybe later lah. Later than 8. Alright, class? We go for itinerary. Okay, I inform you. Ini session 8 kan? Alright. Okay, Assalamualaikum warahmatullahi wabarakatuh. Scan your attendance. Okay.